So far, we've learned two methods to find or evaluate limits. Those two methods are graphically and numerically. This third method is finding limits analytically. Analytically basically just means algebraically, for lack of a better word. And we're going to have a couple different methods under this particular method of limits analytically. And in just a moment, we will kind of make a sort of graphic organizer to show all of this as well. Let's just start by taking a look at what it would look like to find a limit analytically, aka algebraically. We see that we have a couple examples here, 1 and 2, and 2 parts in each because they're pretty similar. The first thing that you always want to do is simply just plug in the x value. This works a lot of the time because a lot of the time the functions that we have are just continuous flowy functions, and the limit is simply just whatever the y value is at this x value. Now, if we might run into issues, and we'll explore those later in this video. But for now, let's use this method called direct substitution. That simply means I'm going to plug in pi over 4 everywhere there's an x here. If I get an answer, I'm good. That's my limit. So let's plug it in. I'm going to plug in pi over 4 everywhere there's an x. So I'm going to get pi over 4 times the cosine of pi over 4. The cosine of pi over 4 is root 2 over 2. So we'll have pi over 4 times root 2 over 2. And our final answer will be pi root 2, kind of weird, but we can write it that way, over 8. In part B, we're going to also use direct substitution, and I'm going to plug in pi over 2 now everywhere there's an x. I'm going to have pi over 2 times the cosine of pi over 2. Now the cosine of pi over 2 is 0, so we'll have pi over 2 times 0. That is 0. 0 is a completely fine answer to get. It's still just a number, just like this guy is up here. It's a real number, and this is a fine answer. Now, we'll see that if we divide by 0, that gives us an issue. All right, let's take a look at number 2. We have a rational function. X is in the denominator. So there's potentially an issue, right? Our denominator could be 0. Well, let's take a look at that denominator. If I plug 5 in, I'm not going to have a problem. We'll have 9 as our denominator. So let's use direct substitution. We'll have 2 times 5, 10, minus 3. So our numerator will be 7, and our denominator will be 5 plus 4. So our answer is 7/9. Now take a look at part B. There's a reason that I used this x value here. Let's think about why. Because if we plug in -4 for x, we clearly will have an issue in our denominator. Let's go ahead and use direct substitution anyway. Plugging in -4, we'll get -11 in the numerator and 0 in the denominator. When we have a non-zero number over 0, that is undefined. There is not a solution for this. So we would say that this limit does not exist. Now, we'll explore shortly if we get 0 over 0, that's something called indeterminate form, and we can analyze that a little bit further with some other methods. Let's create this graphic organizer. We will continue to fill this out throughout the video. We've already determined the 3 ways to evaluate a limit are graphically, obviously with a graph and just kind of using our visuals there, and numerically. Numerically is with a table of values. That one is not as exact of a science, and neither is graphically really. Graphically, again, we're just being visual about it, so it's not always exact. This is obviously with a graph. And then our third method that we're learning about right now is analytically. This is like the exact science of it all. Now, there's multiple methods under the analytical method. We found the first one, which is always what you should do first, which is direct substitution. And that literally means we plug in that x value in. If we get an answer out, we're good. So our first step when we're doing it analytically, I did change this to a 1, is that we're going to use direct substitution. If we get an answer, we're good. We found the limit. If we get a non-zero number over a 0, which we saw in the previous example, that means our limit does not exist. And then finally, the last thing that we're going to possibly get, so we could either get an answer, a numerical answer, a non-zero over a 0, which means our limit doesn't exist. We can also get 0 over 0. And that is what's called indeterminate form. Now, usually, and the calculus that we're going to see, this does mean that the limit still exists. We just have to use other algebraic methods in order to find it, since direct substitution failed. Those other algebraic methods, we're about to explore them now. Here again, we have two examples, each with a part A and B. If we look at 3A, we see that this is definitely an analytical method. We have just a function here, so let's just plug it in. Let's try direct substitution first. Let's see how it goes. If you plug in 3 here, we'll have 9 minus 15 plus 6, that's 0. And if we plug in 3 down here, we'll get 2 times 9, 18 minus 18, that's 0. So we are getting, using direct substitution, we're getting 0 over 0. That means we have indeterminate form. That means that we need to use another algebraic method in order to evaluate the limit, because the limit most likely still exists. What happens here is that there's most likely a hole in the graph, but our limit still does exist. So the method that we're going to use here is factoring. We can see that this is a rational function once again, and both the numerator and the denominator are factorable. So let's go ahead and factor both the top and the bottom here. So we're going to get the limit as x approaches 3, and then our numerator is a quadratic trinomial. It can factor into x minus 2 and x minus 3. And our denominator, we're going to take out the 2. If we think about when we take out the 2, we're left with x squared minus 9, which is a difference of squares. So that'll factor into 2, x plus 3, x minus 3. Now, I haven't changed anything per se. Like I changed the way it looked, right? We went from standard to factored form, but I still have the same issue. If I were to plug in 3 again, I would have 1 times 0 in the numerator and 2 times 6 times 0 in the denominator. It's still 0 over 0. However, we can see now, and you might be able to tell what we're doing next, is we're going to cancel out our issue. The x minus 3's will cancel top to bottom. Now we can do this. This just means that there's a hole in the graph at x is 3. This is called a removable discontinuity. But we've removed our error. We've removed what was making this 0 and 0. So now what we're going to do is, with our sort of simplified function here, is we're going to do direct substitution again. So we can plug in 3 now because we're no longer going to get 0 over 0. So let's plug in 3. So we'll have 3 minus 2 in the numerator, and we'll have 2 times 3 plus 3 in the denominator. This will give us 1 over 2 times 6, so 1/12. And that is our limit. This function right here has a hole at the coordinate point 3, 1/12. However, our function is still approaching it on either side of 3. Let's take a look at part B. I switched up just a little bit, but it's kind of the same idea. So again, a rational function. Let's first try direct substitution. When we plug in 3, we'll get 0 over 0, indeterminate form. That means that I need to use an alternate algebraic method, and factoring is the one we know so far. Factoring and simplifying. So let's try some factoring. We cannot factor the numerator, it's already simplified. However, we know how the denominator factors, which is just like this. And now we can see that what's able to be canceled is, again, the x minus 3's. But be careful, the numerator still has a 1 in it. So I want you to realize that this is really, we'll do down here, this is really the limit as x approaches 3 of 1 over 2 times x plus 3. That's a common mistake students will make, is they will just forget that this is a fraction and forget that there's a numerator. Now we can use direct substitution since our issue has been removed. 1 over 12 is our answer once again. So these two functions are going to look slightly different, but they're going to have the same general shape. All right, let's take a look at number 4. We once again are going to go through that same process. So the first thing that we're going to do is plug in with direct substitution. When we plug in 2, we'll get 0 over 0. So we're going to use an alternate algebraic method, which in this case is factoring. We can't factor the numerator, but I'm going to just hold on a second with the numerator because it's 2 minus x, and we normally will see x minus 2, so it's a little bit swapped. The denominator is simply a difference of squares. Now, I clearly want to cancel x minus 2. That's what I want to cancel top to bottom, so then I can plug in 2 and it won't be an issue. Well, this isn't x minus 2, it's 2 minus x. But let's take a look at this. Let's factor out the negative up in the numerator. So if I factor a negative out, let's think about what we're left with. If I factor out a negative 1, I would be left with negative 2 plus x. That can simply be rewritten as negative and then x minus 2 in parentheses all over x plus 2, x minus 2. The reason we did that is so the x minus 2's can now cancel like we need them to. So that's just a little mathematical trick you can use when you need to swap things around, is just factor out a negative 1. So we do have to realize here that when we're now using direct substitution, and here I'll write it out one more time, this is now the limit as x approaches 2, and what remains in the numerator, similar to our last example, is not a 1 now, but a negative 1. And then x plus 2 in the denominator, we can now use direct substitution and plug in 2. So we'll get negative 1/4 as our limit. And our last one here in the factoring realm is part B. So again, pretty similar. But let's realize now that we're plugging in negative 2. So the first thing we want to do once again is direct substitution. When we do direct substitution, we'll get 2 minus negative 2. That'll give us 4 up top. Plugging in negative 2 in the denominator will give us 0. Recall that when we have a non-zero number over 0, that's not okay mathematically. We can't take a non-zero. We can't do 4 divided by 0. So this means that our limit does not exist. Let's check back in for a moment with our graphic organizer and zone in here on the analytically, sort of like steps here. So again, our first step always is to just try direct substitution. Sometimes we get a good answer. We just get like a numerical answer. Awesome. 0's fine. 0's a number. Cool. Good. Now, when we come into issues is when we have 0 in the denominator. So if we have a non-zero number over 0, that doesn't work mathematically. We say the limit does not exist. We're done. But if we have 0 over 0, this is where we could go further with indeterminate form. This means most likely that the limits still exist, and we need to explore other mathematical roots. The one that we just learned is factoring and simplifying. Now we're going to learn one other algebraic method for if we get indeterminate form, and that one is called rationalizing. We will do a few examples using rationalizing or the rationalizing technique to evaluate a limit, and those are really the main two algebraic methods for when you get indeterminate form. Are there other ways to evaluate limits? Yes, it's not an exact science. You have to mess around quite a bit, but those are the main two that we're going to be focused on. In the next video or the coming videos, we will also talk about some common like trig limits, and that's also a way that we can find limits analytically as well. But these are the main two algebraic methods that we use when we have indeterminate form. All right, 2 more limits to evaluate, and as a treat to you to end the video, no parts A and B. All right, let's take a look at number 5. Again, first step, ding ding, plug in 4. So we want to use direct substitution. We're going to get the square root of 9, 3 minus 3, 0, over 4 minus 4, 0. So we get indeterminate form. Who would have guessed? So because we have indeterminate form, I'm going to erase this here. Because we have indeterminate form, we need to use an algebraic method to evaluate the limit, since it most likely still exists. Well, this is clearly not factorable, but in this case, we have square roots. When, in general, if you do see a square root after you've gotten indeterminate form, you most likely will need to rationalize. Now, to rationalize means to make something rational. And so what we're going to do is realize here the issue is up top. We no longer want this irrational, this root up here. So we're going to multiply the top and the bottom by the conjugate of the numerator. The conjugate of the numerator is simply switching this sign right here. So the conjugate that we're going to multiply by, top and bottom by, is root x plus 5. Note that that sign didn't change. And then plus 3. And we're going to multiply both top and bottom by that, because when you're working with fractions, you got to keep it fair. Whatever you do to the top, you do to the bottom. Okay, this is going to take a little bit of algebra. So when we multiply here, anytime you multiply a binomial times another binomial, right, two terms, you FOIL, or you distribute through. All right, so we theoretically will have 4 terms here. However, when multiplying a binomial by its conjugate, again, that's the conjugate right here. That's the only thing that changed. Those two inside terms cancel each other out. And so we only have to multiply the first times the first and the last times the last. Again, that is only a shortcut you can take when you're multiplying something by its conjugate. So let's think about what we're doing first. We are taking root x plus 5 times root x plus 5. Hey, I'm squaring root x plus 5, right? I'm multiplying it by itself. So that just means I'm left with x plus 5. I took a square root and I squared it, essentially. So I'm just left with the radicand, what's inside. Then I'm going to multiply the negative 3 times the 3. I'll get minus 9. Easy peas. Look, I rationalized it. No longer is there a root. Now, in the denominator, we are not actually going to do any multiplying anything out. And here's why. This is kind of just a little calc trick. All we're going to do is simply rewrite the denominator as these two factors, I suppose, or these two binomials here. We'll see why. Let's take a look at the numerator. The numerator can get cleaned up to just x minus 4. So I'm actually going to do that right now just by erasing it. So that numerator is really just x minus 4. And look what ends up happening is that the x minus 4s end up canceling. Just like the factors canceled in our factoring and simplifying technique. So what we're left with essentially is the limit as x approaches 4 of 1 over root x plus 5 plus 3. And now direct substitution won't fail. It'll work now since we won't get 0 over 0. So if we plug in 4, we'll actually get 1 over square root of 9, which is 3 plus 3. So we'll get 1/6 as our limit. Let's try one more example of rationalizing. This one's very similar. I got slightly ahead of myself because, again, our first step, direct substitution. If we plug in 0 to this, we will get the square root of 1, which is 1, minus 1, which is 0, over 0. So we did get indeterminate form. We need to use an alternate algebraic technique, and in this case, it's going to be rationalizing. So our rationalizing technique, we're going to multiply the numerator and the denominator by the conjugate of the numerator here. And we're doing the conjugate of the numerator because the numerator root's in it. So again, conjugate is simply switching up this sign. Now I do realize that both of our examples so far started with a minus sign, and so our conjugate had a plus in it. If we had started with a plus here between the two terms, this would obviously be a minus. So a conjugate is just the opposite sign in between the two terms. And whatever we multiply the numerator by, we must multiply the denominator by. Math rules. All right, let's go ahead and do our multiplication. Again, when we multiply two binomials and they're conjugates of each other, you only need to do the first times the first and the last times the last. First term times first term, it's going to be root x plus 1 times root x plus 1, which will just give us x plus 1. And then negative 1 times 1 will give us minus 1. In our denominator, we're not going to multiply anything out. We just don't need to because we will cancel. So we can see the numerator cancels down to just x. So if the limit as x approaches 0 of x in the numerator, and we can see now what's going to cancel, which is the x's. So our x's will cancel. There's really a 1 left on top here, and now we can use direct substitution. Direct substitution will yield a 1 in the numerator. When we plug in 0 for x down here, we'll get 1 plus 1. So this will give us 1 over 2 with direct substitution, and our limit is 1/2. We're going to just pop back into this graphic organizer to close out the video. Be sure that you have this written down somewhere in your notes. It doesn't have to look exactly like this. Hopefully it looks more organized, but this is the main idea so far with evaluating limits. These ones are more visual, looking at a graph, looking at a table. This is far more, paper, pencil, doing algebra. And this is the one that we're going to focus on the most, and probably the one that students struggle with the most just because of all the algebra involved in both of these techniques. All right, if you realize you need to brush up on factoring or any rationalizing, do some practice problems, go through those examples again, check your work. Good luck.